In this video, we are going to do a concavity example with a derivative graph that's given to us. So here is the example. We have this graph, and this is the graph of y equals f prime of x. So it's the graph of the derivative. And in part A, I want to find the intervals where the original function f is concave up and concave down. Okay, so I want to first have you try this question. Even though we haven't done an example before that's like this, I want to see if you can apply the concepts that we've learned about related to concavity and second derivatives to answer this question. So pause the video for about 2 minutes to try this question on your own first. So 4, 3, 2, 1, pause the video. Pause the video for 2 minutes to try this. Alright, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to try this. So let's talk about it together. So if we're trying to find when our function is concave up, our function is going to be concave up if and only if. So this is a symbol that stands for if and only if. So that's another way of saying I'm about to write something that's equivalent to what I just wrote. So my function being concave up is equivalent to the second derivative being positive. So that we've seen before. Our function is concave up when the second derivative is positive. And that, well, what does that mean? What is this equivalent to? So if the second derivative is positive, that means something about the first derivative. What does it mean about the first derivative? It means the first derivative is increasing. The reason for that is, think about the first derivative. Think about this graph as just a function. This is just some function. When this function is increasing, that means its derivative. So it means the derivative of f prime, aka the second derivative. So this means the derivative f prime, aka the second derivative, is positive. So when something is increasing, in this case it's f prime of x that's increasing, that means its derivative is positive. Well, the derivative of f prime is f double prime. And that's what the previous statement said. It said the second derivative is positive. So that's where this equivalency comes from. So all we're looking for is when the first derivative, which is this graph right here, when is this graph increasing? So I just look at the graph to determine that. So this happens on the intervals from -2 to 1, and on the interval from 3 to infinity. Those are the intervals where this function is concave up. Sorry, where the original function is concave up, because that's where this derivative graph was increasing. Okay, so on the flip side, okay, so our function is, original function would be concave down when the second derivative is less than 0 when it's negative. And that would happen when the first derivative is decreasing, because when the first derivative is decreasing, that means its derivative, which is the second derivative, would be negative. And that's what the previous statement says. Okay, so I have to look at my derivative graph and just say, when is this thing decreasing? Well, this thing is decreasing on the interval from -infinity to -2. So -infinity to -2. And it's also decreasing from 1 to 3. So from 1 to 3. And that's my answer. So this is the interval where it's concave up. And that is the interval where it's concave down. Concave up, concave down. All right, let's do part B of this example. Let's find inflection points. Okay, so I've copied down this graph again, and let's use this to now find the values, x values of the inflection points. Okay. So remember that inflection points are where we need two things. F, the original function, switches concavity, so from concave up to concave down, or vice versa. So f needs to switch concavity, and f, the original function, needs to be continuous there. So it's not enough for it to just change concavity. The original function also has to be continuous there. Okay. So our function being continuous, this is actually guaranteed in this example. This is guaranteed since f prime, we are given the graph of f prime, and f prime exists, it's defined everywhere based off of the graph. And when a derivative exists, when f prime exists, that means f is differentiable. The fact that f is differentiable, so differentiability, that property, that implies, this arrow means implies, differentiability implies that f is continuous. It implies continuity. So this arrow means implies. So that's a theorem that we've stated before. When a function is differentiable somewhere, it is continuous there as well. In this case, because the derivative graph is given to us, we know the derivative exists everywhere. That means our original function is differentiable everywhere. And because f is differentiable everywhere, that means it's continuous everywhere. Okay, so we don't have to worry about the continuous part. Our original function is going to be continuous everywhere. Instead, we just get to focus on where does f switch concavity. Okay, so where does it switch concavity? Well, that happens at -2. At -2, what happened? For example, at -2, our function switched from concave down, because the derivative was decreasing before -2, to concave up, and the derivative was increasing after -2. Okay. So that was one value where the concavity switches, and then it's also 1, and then it's also 3. And those are going to be my answers. So the key idea was, because we were given the graph of the derivative, in terms of this graph, the original function switches concavity when f prime changes from increasing to decreasing, or vice versa. And that's actually what we ended up looking for here. That's what happened at -2, at +1, and at 3. The derivative graph changed from increasing to decreasing, or vice versa. All right, so in terms of our goals, we have finished our last goal for this section. We did an example where we were given the graph of f prime, the graph of the derivative, and used that to find the intervals where the original function was concave up and concave down.